allow us much better environmental performance for copper making than some 50 years ago. So copper is made out of mostly out of chalcopyrite ore, which is iron copper sulfide. And in the past, it was smelted in many steps, but nowadays there are only matte making and converting steps, and these three issues, so raw material, its chemical composition, and the present technologies, so they mean that the main product in terms of tonnages of a smelter, as I mentioned last week, is actually sulfuric acid. And next biggest is the slag. And third is this pure copper. So we and smelters have cost issues with the slag storage and landfilling, and then they have costs with SO2 fixing, which sometimes is not profitable and has been limiting in the past the use of copper smelting in copper making, because the sulfuric acid market has been so low, and no sulfuric acid has been needed in such a quantities available from copper smelters, nickel smelters, lead smelters, and zinc smelters. So if we talk about copper smelting technologies, we can divide them into two different families or tribes of processing. So we have technologies based on suspension, gas solid suspension smelting, and then we have technologies which are based on smelting in a bath, in molten mixture of sulfide and slag components. These technologies, from chemical point of view, are pretty much similar, and the chemistry in terms of fluxing the forming iron oxides is almost identical. So how these technologies then differ from each other is the yield of copper, how much copper is obtained from the raw materials in one pass, so primary yield. Then heat balance is different depending on how the smelting is carried out, and also the feature of online availability is different depending on how these reactors and furnaces must be relined, and how often they must be stopped for maintenance procedures. So here we have a typical bath smelting reactor, and these bath smelting, and this is a second one, these bath smelting vessels or furnaces are separated from each other by the fact how this oxidizing gas is introduced in the vessel. So it is it is introduced in the molten bath either by movable lance, which is here as a dark bar, or as submerged 2 years, which may be simple tubes introducing the gas in the bath, or shrouded multi-gas systems which are using high pressure air and oxygen flow. So basically, and in somewhat simplified form, we can say that sulfide smelting is very much a question on how we manage the fluxing. Fluxing means how we convert solid iron oxides into molten iron oxides, and often, if not in all cases, the smelters have the aim to really maximize this primary yield of copper. So fraction of copper received when copper matte is tapped from the furnace, and this is technologically important, and important also, very important also economically to the industrial operations. So what is the kind of challenge in all sulfide smelting operations? It is the high fraction of iron present in copper concentrates and in nickel concentrates and sulfide concentrates as well. And this means that we are producing rather high volumes and masses of slag, so that our slag to copper ratio is today typically larger than 2 by weight, and it's increasing all the time because of decreasing copper ore grades and copper concentrate grades. And when we have kind of historical perspective in copper matte smelting, so we see that such device, which was the dominant furnace in making copper matte some 50 years ago, the reverb or reverberatory furnace does not exist as industrial furnace anymore. It is few of them are in use, but most of them have been replaced by other technologies, and mostly by flash melting, which is generating more than half of the world copper production. And then we have lots of these bath smelting processes which have different names, like TSL, it's a generic name, top submerged lance smelting. So then we have Noranda and El Teniente converters, we have Mitsubishi furnace, and these bottom blown SKS reactors. So we have lots of technologies in copper making compared to iron and steel making, where practically one single technology is used for hot metal smelting, and then for steel making. Because of the mineral composition of copper sulfide concentrates, we can smelt, we can process these concentrates without external energy. And what is needed for that is that we have enough combustible sulfides in our concentrate. So typically they are chalcopyrite, but then there are also pyrite, in certain cases pyrrhotite, so iron sulfides, and then complex sulfides carrying some impurities like tetrahedrite, tennantite, and similar copper and some other metal double sulfides which generate energy when they are combusted. So here we have a schematic, and it's not only schematic, which is showing on the left-hand side, it is showing how much energy is generated when we are smelting copper from a certain concentrate to matte grades from 50 to 70 percent copper. And then on the right-hand side, we see which components of the outcoming substances kind of get that reaction heat. So we have this is a case of copper matte converting, where we have blister, we have slag, we have nitrogen from the feed, we have dust and heat losses and other energy consumption. So these reaction heats and requirements of energy in the product side, these can be calculated by thermodynamic handbooks and values of property values of those phases produced in the smelting vessel. We use in copper making one phrase which must be explained in this stage. That is the copper content of the matte, which is called matte grade. And matte grade in copper matte making is directly connected with the iron content or concentration of the matte. So this is equilibrium calculation made at smelting temperature of 1325 in pure SO2 as the off gas, and there is a fixed 30 weight percent SiO2 silica concentration in the slag. So you can see that correlation between the matte grade and iron in matte is linear, and it is pretty nicely so, and this means that we can use the actual oxidation degree of the system of the matte is its iron concentration, but we can use this copper concentration of matte as a measure for indicating how far the the oxidation has been proceeded during the processing. So this is how smelters are dealing those mats. They don't talk about copper concentration of matte. They always talk about matte grade, which means copper concentration, but it is related to the iron. So what happens there in the smelting furnace in all these technologies? So we have copper iron sulfide chalcopyrite molecule reacting with oxygen and generating iron oxide, sulfur dioxide, and then a matte phase which has different fractions of iron. So this X here in the feed side of the system is also meaning that the matte grade we are generating is dependent on the oxygen amount we feed into the furnace, and then it also affects the amount of iron oxides formed, and also to the silicon dioxide, so quartz additions needed into the furnace to maintain a certain composition of the forming matte smelting slag. So these are all interconnected, and as you saw in the previous slide, also the heat generated is interconnected with this simple and straightforward reaction here. So we have, in copper making, we have two phases which are of importance, and what we generate in the smelting vessel is the valuable one is copper matte. It is in practice it is a mixture of copper sulfide and iron sulfide, iron monosulfide, and this is the phase diagram showing how liquid phase expands at elevated temperatures from pure copper sulfide to pure iron monosulfide. So we see that below 1200 degrees C, copper matte is always at all compositions. It is always molten. So we don't have any kind of fundamental problems with the matte phase. It is always molten when we are smelting copper matte, and it's as an ionic melt, its viscosity is rather low, so we can expect that we don't have any major problems with the fluidity of these matte phases, whatever composition we have from about 40% iron, 50% iron sulfides to 0. So about 1200, these mattes are molten. So molten mattes at copper matte smelting temperatures, they have relatively high sulfur pressure. This is problem to certain technologies, and you can see from this phase diagram and sulfur pressure diagram that depending on sulfur concentration. So this is copper sulfur line, and this is iron sulfur line. The sulfur, elemental sulfur pressures may be relatively high. Luckily, we don't have, this is a mineral mixture from copper sulfide to iron monosulfide. Luckily, we don't have such high sulfur concentrations as iron monosulfide has in copper making. So our sulfur pressures typically are of the order of 1%. This is logarithmic square root of PS2. So 1% is enough to make problems in certain technologies, but it is always a feature which is important in math making. So this means that fluxing and which kind of slag we are making in copper matte smelting, it is the key issue in practical operations. And in copper making as well as in nickel matte smelting, we, without exception, we use silica for SiO2 for fluxing the forming iron oxides. And this is a ternary phase diagram with liquidus isotherms from 1150 to 1400 C, showing the development of the liquid slag domain. The lowest melting point is somewhere around 1150, which is a bit below the copper rich copper matte melting points. And then another thing which is important to notice here is that this diagram, which is part of the full diagram, so from FeO to Fe2O3 and further on to pure silica, it is only fraction of it. So this liquidus line here shows the saturation boundary, the primary phase field of magnetite, and it indicates that magnetite, so trivalent iron oxide, can dissolve in significant weight fractions in the slag. So more than 20% in industrial copper smelting conditions. And how this oxidation process is going on. So it is a homogeneous process in the slag where divalent FeO is oxidized by oxygen to iron 3 plus, which is here written as a so-called monocationic species. It's half of Fe2O3, and this reaction takes place always in copper and nickel smelting condition, matte smelting conditions, and the composition of the slag is maintained within such ranges that magnetite, solid magnetite saturation is never met. So when the productivity of copper smelting technologies was increased very much from the reverb era, 1940s, 50s, until 1970s and 80s, when flash smelting was gaining applications and popularity. So also the matte grade tapped from the matte smelting furnace has been increased from about 40 to 50% to 60 and 70% of today. So that means that the oxygen pressure, this here on the left hand side, it has been increased in the smelting furnace, and that means that the magnetite or 3-valent ferric oxide concentration in the slag has been increased. Why this is important? It is important from two reasons. First one is that your slag is approaching but not reaching that primary phase field area. And second one is that when you start cooling down your slag, so magnetite is the primary phase of your slag, and magnetite is known by experience to precipitate quickly from the slag when it cools, and actually it's prevention of that precipitation is rather difficult if you try in laboratory conditions to quench your iron silicate slag fast enough to reach a situation where magnetite is not precipitated from your slag. You need rather high quenching rates and small samples to maintain that quenching rate as well. So that is how you see magnetite in all matte smelting industrial matte smelting slags, and you can also use that fast precipitation rate of magnetite in real industrial conditions, because if you sample copper or nickel melting slag with a spoon and allow it cool down in the spoon without quenching it or granulating it, so the precipitation of 3-valent iron as magnetite is essentially quantitative. So you can get your all your 3-valent iron from the glassy phase and measure how much 3-valent iron you have or had in your smelting vessel, and this is utilized in industrial conditions because measurement of this magnetite concentration is rather easy. It is magnetic and can be measured quickly and in a reliable way. This Gibbs triangle shows oxygen isobars of an industrial slag at 1300, and here we have the molten slag domain oxide liquid, which is divided in the oxidizing conditions by this primary phase boundary from spinel saturation, so from magnetite saturation. Up here we have the silica saturation, and here we have reducing conditions of iron saturation. This is a true industrial slag with some potassium, some lime, and some alumina as well in it. So it is fundamentally different from the pure phase diagram I showed you a couple of slides earlier. But what is important here is that these oxygen isobars are going through this fully molten slag domain, and when we increase silica concentration, so when we go towards that silica corner, or when we oxidize the slag, adding some more trivalent iron in the system, always our oxygen activity or oxygen partial pressure of the slag is changed. So it is not only one condition we have here in the molten slag, but several conditions, and these conditions generate different copper grades in the copper matte. So to summarize what I said a few seconds ago, I could simplify that all copper smelting slags are homogeneous liquid phases, even if they contain trivalent iron, or even if their magnetite concentration is 15 to 20%, they are still at smelting temperature. They are homogeneous liquid phases, and that through composition is affected by how we are fluxing the slag, how much silica we add into the slag. And this is a equilibrium calculation of a specific slag from industry, which has been generated at a fixed copper grade, but varying silica concentration into slag. So when we put more silica into slag, we change the activity coefficients of iron oxides in there, and then we change the solubilities of ferric oxides in the slag. So if we add more silica into the slag, we decrease the ferric oxide concentration in the homogeneous slag. That means that we increase its activity coefficient, because in here we have a fixed copper matte with fixed oxygen and sulfur activity in the system. So with these freely selected variables in copper smelting, we have we have a large number of different conditions which are generated by the smelting vessel, depending on its fluxing rate or fluxing type, how much silica we add in there, and what is the smelting temperature, and also which kind of copper matte we are producing in the vessel. So there's no single operation point or end point of the smelting. All these phenomena are interconnected, and you must be aware of all these details before you start analyzing your smelting operation and its conditions. In all matte smelting and also in all metal smelting conditions in general, we have two types of losses in the primary and secondary smelting steps. We have chemically dissolved metal, in this case copper, in the slag, and then we have mechanically entrained copper, whether that is matte, like in this matte smelting case, but in secondary smelters and in copper converting, it may be also blister copper. So the chemical dissolution of copper is driven by a simple equation, chemical reaction, where copper is oxidized by oxygen, and the formed oxygen, copper oxide, is dissolved in slag. So there is a direct link between the copper in slag and oxygen partial pressure of your system at a certain copper activity or certain matte grade or metallic copper activity in the system. So this is straightforward, and what is not straightforward is this mechanically entrained copper in industrial slags. We have typically more of mechanically entrained copper in industrial slags than chemically dissolved, and in some cases it may be 4 times or of the order of magnitude. But in typically flash melting processes, in matte making mode, our typical entrained copper is of the same order of magnitude as chemically dissolved copper. So we have two types of things there when we look at how copper losses are formed in matte making. All high temperature processes also generate flue dust, and that flue dust is carried from the smelting vessel as one component of the off gas. So we may have mechanical entrainment of particles in the off gas, and this is particularly the case in flash melting or in more general way in suspension smelting technologies, where typically about 5% or more is entrained in the off gas. And the second way of generating flue dust is by low boiling point substances such as arsenic, antimony, bismuth, zinc, which exist at high temperatures as gas components in the off gas, and then they are condensed at low temperatures and form typically in the off gas drain. They form fine dust, which is rather tricky to treat in the gas drain. So many flash melting operators tend today to recirculate this flue dust back to the feed mixture, and what is the chemical consequence of this mode of operation is that those smelters are forcing all these low boiling substances to two streams coming from the smelting vessel, and in copper smelting it is the slag or the matte, and in the copper smelter it is either the final slag or the anode copper, because nothing else is actually coming out in large quantities from the smelting vessel. So this kind of operation is increasing the impurity levels of the anodes and the discard slag, and that it may have problem in the refining stage of the copper making, but it has negative impact on the usability of slags in copper making in general, also in nickel making in general. So how copper is today made in the world? So some 20 years ago, we had more than 50% of the capacity, which does not mean the production, but the capacity available for production. So almost 60% was available for copper making in the world using the flash smelting, and 20 years ago we had some reverb still, and then we had modified reverbs and also in those years also electric furnace smelting, which is today disappearing, and also these reverb smelters are soon obsolete, because no sulfur capture can be done in their off-gas systems. But it is estimated by World Copper Fact Book, so the International Copper Study Group, that this flash smelting type of technologies will be increasing their share in the future, and let's go and look at what these technologies are and which kind of processes and chemistries there are in the suspension smelting technology family in general. So originally, flash melting was invented some 70 plus years ago because of shortage of energy, and the inventing company was forced to use something else than electric smelting, and they started studying this kind of new technology where the chemical energy of the concentrate was utilized, and it needed invention of a furnace which is not today used for anything else but flash smelting and flash converting purposes, and it was totally novel 70 plus years ago. It has two shafts. Height of these shafts are about 8-10 meters. The first one here is the reaction shaft, where all these reactions take place, and the next shaft is uptake, which takes care of the off-gas outlet, and between them is a horizontal vessel called settler. And if, as I will show you later, if we look at the smelter, whole smelter and its unit operations of various kinds, this flash smelting furnace is only very, very tiny part of the smelter. It needs a lot of auxiliary instruments and operations to be able to operate. So the essential parts of flash melting unit is actually the concentrate burner, and then reaction shaft, settler, uptake shaft, and the boiler system, which is actually much bigger than the smelting furnace itself by volume, and then electrostatic precipitator, which is important for cleaning the off gas before it is led to acid plant and sulfur fixing for making sulfuric acid, and if needed, liquid SO2. So we will examine these parts in detail with the following slides. So this is a cross section, computational fluid dynamics study of reactions taking place in a flash melting furnace, and what is important for this suspension smelting technologies is that the process needs dry feed, because moist feed cannot generate solid gas suspension, and there's no way to distribute this solid gas suspension throughout the cross section of this reaction shaft. So what happens in the reaction shaft is that these small particles of the feed mixture, which is which is a composite of various concentrates. It may be from several mines. They are mixed together and sometimes mixed with silica sand and also with flue dust, and they are dried beforehand, and then they are distributed in the reaction shaft by so-called concentrate burner, and that concentrate burner is mixing solids and gas with fixed proportions, and at some point in the upper level of this reaction shaft, the small particles of the sulfide minerals ignite, and they start generating heat, and this heat is transferred to the gas and further on to the other particles by radiation and convection, and during that so-called free fall from the burner down to the settler, which takes 3 seconds or something, the surface temperatures of these particles they rise very much. Originally, they are at room temperature, and when they hit the settler material floating there, their temperatures may be from 1600 to 2000 degrees centigrade. At the same time, all oxygen is consumed from the feed gas, and then we have hot particles falling down from the reaction shaft, and gas which is containing the nitrogen fed as the process gas, and all oxygen bound to SO2. So it's nitrogen SO2 mixture which is entering the settler. And how we can figure out those temperatures, we have been measured those temperatures, we have been collected material from those suspensions in pilot furnaces and also from real industrial furnaces, and we have done laboratory scale studies and seen that particle temperatures are higher than the melting point of magnetite, which is 1600 plus. So this is the concentrate burner, and it has distributor for solids and gases here, and it makes the feed mixture in right proportions, which I will tell you after a couple of minutes. So all heat in the flash melting process is generated in the reaction shaft. So it's very hot. It is lined with copper coolers, cooling elements where water circulates, and there's practically very little refractories in the hot side of the construction. So all heat is generated here, and it is enough to melt sand, to melt and decompose flue dusts, and maintain the smelting temperature of this settler, which is typically 1300 C, maybe a bit more or a bit less depending on the circumstances. So this rather generalized pattern indicates how important well-performing concentrate burner is in a flash melting furnace. If it does not generate evenly throughout the cross section, this gas solid suspension, it is seen very quickly that the matte grade is not constant. Flue dust generation is large, and also in the oxygen usage. So off gases start to contain oxygen because all oxygen is not consumed in here. So what happens to those particles falling down from the reaction shaft? This is the surface of the settler liquid bath, and those particles coming down from the reaction shaft, they collide with the settler liquid, the slag or slag matte mixture, and they start reacting with each other. So the actual formation of matte and slag is taking place in the relatively thin layer of the settler, say within depth of, in big flash melting furnaces, of 15-20 centimeters only, and the slag and matte are generated in that point below the reaction shaft and separated, so that the more heavy matte is falling down, and lighter thiosilicate slag is reacting with the solid silica particles, and the final slag is formed in there. So you can guess that this falling suspension from the reaction shaft is rather heterogeneous, because all copper concentrates come from flotation milling processes of the mines. That means that there are large particles and small particles, and then there is gangue, which is not separated probably fully, so from the sulfide minerals. So there are particles which are partly sulfide, partly oxide, and that means that small particles will react first will ignite first, and will be combusted first in the reaction shaft, and the big ones we have defined the kind of limit. So 0.1, 0.2 millimeter particles, they don't ignite at all. So there is a mixture of non-reacted, non-oxidized sulfide material and fully combusted oxidic copper and iron material, which then reacts on the surface of the settler products. And as Imam told last week, this Akira Yazawa's diagram is a good tool for analyzing various phenomena in copper making, because it typically takes place at single temperature and under single SO2 partial pressure, depending on the oxygen enrichment of the system. So typically we are between SO2 partial pressures of 10% to 100%. So between these lines, and from matte smelting, we approach from here towards the copper stability range, so that we are probably around that point in real industrial copper matte making, producing 70% copper in the matte. And the rest of the process from here to there is the converting step, which is chemically much more wide, but technologically and process-wise much so less complicated from many reasons. So this diagram clearly shows the equilibrium points of the matte slag systems at various matte grades, and the limiting boundaries of magnetite, iron, and silica saturation, which are not meant to approach in industrial copper making. So flash melting technology is very flexible because it can be adjusted to produce wide range of matte grades. And this is because of the rather tall reaction shaft. We can adjust certain operational parameters within the heat balance of the furnace quite freely. So once the heat balance is okay, once the heat generated by the sulfide combustion reactions is enough, we can adjust whether we are producing matte grade of say 67 or 72, or even lower, from 50% to 72 if needed. And that specific feature of the reaction shaft is the length of the time, how much particles need to fall down from the concentrate burner down to the settler. So that from 2 to 3 seconds, it is enough to adjust the reactions in such a way that all oxygen is consumed, and if we feed less oxygen in the reaction shaft, we oxidize less the feed mixture, and we produce lower matte grade than before. So we have the variable of oxygen coefficient as a practical tool for adjusting the matte grade. So if we feed more oxygen, we oxidize more iron, we oxidize more sulfur, and we generate higher copper grade, higher matte grade in copper matte, and vice versa. So here I have an example of some industrial or commercial concentrate mixtures with various copper grades in the feed mixture, and what kind of oxygen coefficient, so expressed as normal cubic meters of oxygen for each ton of concentrate is needed for producing different matte grades. So it is practical variable used in copper smelters for adjusting copper grade, because the subsequent downstream processing steps need to know what is the matte grade of the coming matte for converting step. So what is essential in sulfide smelting today is the ability of the technology to treat the off gases and to capture the sulfur dioxide produced. So this is important because we don't want to increase or generate acid rain in the world. And the convenient way of avoiding that is to generate sulfuric acid, which is a widely used commodity and which can be sold to chemical industry without big trouble. So these furnaces which are used in sulfide smelting, they have a big gas drain for treating SO2 rich off gas, and that is a costly operation. It is by volume, even if this gas drain is empty, it is by volume much larger than this flash melting furnace alone. But it contains auxiliary instruments like flue dust treatment, and it must be tight. So this is a cost issue in smelter investment, and that is why the total gas amount, so volumetric flow rate of gas, is a major issue in smelters, and it is linked with this off gas treatment. If we have wet feed, like in certain technologies prefer to use and need to use, so their volumetric gas flow rates may be 3 times that of flash melting. So that means that they have 3 times larger investment in the off gas treatment systems, and this is clearly shown in a pie chart, which is showing how much various sub processes in copper sulfide smelting facility take in the total capital expenditure. So sulfuric acid plant is a big share in that pie. Converter gas handling, smelting gas handling, they are not half, but close to 50% of a flash melting, flash converting system. So if we increase by taking wet feed into the system, if we increase the off-gas volume by a factor of 3, we also increase the total expenditure, capital expenditure needed for the decent off-gas treatment, and also the OPEX operation cost will be higher. So these are the side effects of the selected smelting technology, which are related to the smelting itself, but very rarely treated in the literature. So few words about the bath smelting processes. So we have quite a number of technologies in this field which are generally smaller scale operations than flash melting, and they are industrially used in quite much in copper smelting, and they are, as I said earlier, they are either vertical converter type vessels, which then have movable lance for introducing the oxidation gas, or horizontal cylinders where tuyers are either from side or bottom of the vessel. And this is the smelting vessel where you have material feed from various sides of the furnace. Off gas is collected from the same end as the slag, in a similar way as in flash melting, and also white metal, or depending on what is the process, the sulfide, copper sulfide matte is taken from the same end as the feed material. So many of these are resembling the Pear-Smith converter used more than 100 years in copper converting, but some recent developments have high pressure nozzles for gas feed, which have the positive feature not blocking by magnetite accretions when the blowing is continued. So certain cases when traditional 2 years used in Pear-Smith converters, like up here, are used, the 2 year must be opened by punching, by inserting steel rod through this 2 year, and opening the blockage in the hot end of the 2 year. So if we look at full bath smelting plant, it is not very different from flash melting or suspension smelting plant, but there's one major difference which must be kept in mind. So this is TSL furnace. It's waste heat boiler and electrostatic precipitator acid plant here, and then tapping of this melting vessel is to the settling furnace. So these two furnaces are combined in flash melting, but because of the very strong mixing in the TSL, so its products are settled in a separate electric furnace, which needs launders for introducing the molten material in here, and also electrical energy for keeping it hot. So then this settled matte is further treated in Peer-Smith converters as in flash melting. So this is pretty much the same arrangement, and slag is either granulated depending on its end use, or then it may be cleaned in a separate slag cleaning circuit for producing discard slag for landfilling. So in most copper smelters, the matte produced in the flash melting or bath smelting step is then converted into metallic copper, and typical tool here is Peer-Smith converter, which probably is producing 80% of copper in the world, and it is a two-step operation where we have 98-99% pure copper as the product ready for fire refining operations in the downstream. We also have possibility to do this converting step in a continuous mode. This is possibility in large copper smelters, and the Indonesian new smelter, which is under construction, will have this kind of layout. So we have concentrate handling, storage, bedding plant, then drying, mixing and transporting to the flash melting step, where slag is treated in an electric furnace for slag cleaning, and matte is granulated. This granulated matte is fed into the flash converting furnace, which is similar but smaller than this flash melting furnace, and has a similar off-gas treatment system, which both feed sulfuric acid plant. And this flash converting slag is granulated and fed into the primary smelting furnace. So there's no separate flash converting slag treatment as such, because the amount of slag is so small, and it's rather good in terms of its properties to be added in the flash melting, because it contains some 15-20% lime and 20% copper. So copper is recovered, and the lime improves the quality of the smelting slag. As I said, this is mostly used for very big smelters, but the kind of use of flash melting, flash converting combination has been increased over the last 10+ years, so that these lines are nowadays the only ones built for smelters producing about 300,000 tons or more copper per year. So this is very environmental friendly and very economical, high online availability solution for copper making with very small environmental footprint. We also have one option if our concentrates are very high in copper or very low in iron. We have such ores in the world, not many, but they exist, and 1978 first direct to blister copper smelter was started up, and its kind of operation since that has been successful. Second direct to blister smelter was started up probably 10 years later, and then we have couple of more in operation or under construction design phase in the world. So it needs low iron, high copper raw material, which are not common. And this kind of direct to blister smelting is a specific case of copper making, because it makes blister copper in one smelting step, but it's still option for such specific concentrates which are producing, the key is producing little slag only. So this kind of smelter doesn't have grains or converter aisle for transporting molten material, which is outside the flash converting, flash melting lines. It is not seen anywhere. All right, this was my today's talk, and I could now answer some questions, or if you have needs to discuss about details, so please.
Okay, guys. I'm sitting in the lab, Pekka, while listening to you.
Oh, I see.
Okay. Okay, guys. Now it's time for question and answer. So remember, there's always chocolate in each session. So if there is 25 days of course, I will bring you 25, at least 25 chocolate times 200 grams. Can you imagine? 6 kilo just for you. Okay. Okay. Now, please raise your hand and then you can ask your question. Or you can just directly ask to Pekka. Usually students are shy and they need to be pushed in the beginning. Okay, guys, don't be shy. Please just raise your hand or you can directly open the mic. We shall previously we don't have time so many questions. Now it is we have a lot of time, so please ask. You can ask anything, not only about flash melting, about other thing. There's in the text, Becca, in the chat. Very long questions in the
Okay.
chat.
Oh yeah, this is also a good question. So so the issue here is that if there are other processes, yes, actually I was talking only about the pyrometallurgical copper making. In one of my slides of last week, I had a statistics of copper production over the last 100 years, and there was a tiny fraction of copper made by hydro processes, and this is probably 10 to 15% of total production, and not increasing very much because of lack of suitable raw materials. So typically, hydrometallurgical copper copper production needs oxidicores, and they have been mostly used. They are surface layers of sulfide ores which have been oxidized, and the problem here is in hydrometallurgy is that chalcopyrite cannot be leached simply. So it's rather refractory material, and its leaching needs either high pressures or some other tricks. Yes, so there is hydrometallurgical production, but it is not increasing by share because of lack of raw materials. This pyrometallurgical side, yes, we have basically two families of technologies. So the big one called suspension smelting, where most of copper in the world is produced, but then the technologies or names of technologies which are used in bath smelting side, which is much less. It's probably 30% of all. So it is the number of those technologies is large. There are many of those. So as I mentioned in some of my early slides of today, there are these TSL type of technologies, then there are Caldo type of technologies, and also these pure-Smith converter related Noranda El Teniente technologies which are used in Canada and Chile, and also these bottom and sideways blowing technologies further developed from these other converter technologies. There are a couple of side blowing smelters in Russia for copper, and probably also in some other Central Asian smelters using this so-called Vanyukov technology, which is called in China side blowing method. But really, the future will show how these different technologies can compete with each other, and how well they are performing in terms of the critical issues of copper industry. So cost-wise, energy usage, sulfur fixing, sulfur capture, and also these yields, so primary yield and total yield, yields of minority elements, and also capabilities of treating impure and low-grade materials, which is the future challenge in copper making as well. Yeah, I think I collected most of things mentioned in this comment. Yeah, are you satisfied?
Albert, are you satisfied with the answer from Pekka?
Or should I open it somewhat more?
No, it is okay, Pekka.
Okay, good.
Okay, more questions, please. Albert answers yes. He's satisfied. Okay, guys, don't be shy. Please raise your hand and then ask to Pekka directly. It seems that the guys who asking remain constant. So I don't want to give chocolate to the same people. So other guys. Okay. We still have like 20 minutes. Questions? I will check in. Okay. Why everybody so shy now? Okay, Nabil. Nabil?
Okay,
Yes.
thank you to the ma'am for the opportunity. I would like to ask question about continuous copper mate converting, and I saw the flow sheet diagram that after electric furnace, the slag just discard away. Why didn't they recirculate the slag into concentrate dust and slag feeding? Prof. Pekka, thank you.
You mean why the slag? Sorry, why the slag is not circulated back to the smelting? You mean? So you actually cannot circulate it back to the smelting because it contains the iron of the feed, and you must remove that slag in order to remove the iron from the smelting circuit. So it's not it doesn't work like that. So the slag amount would increase, and it would cause problems to the capacity of the smelter. But if you meant that why this slag is discarded, it is not reused. So yeah, that is a very good question, because at least in Europe and US, my feeling is that no copper slag is used because it is classified as not stable, as not stable material for making cement or something like that. So I know that in some countries authorities allow the use of copper slags, but in most European countries it is not allowed, and that is because it contains some zinc, some arsenic, some antimony coming from the raw materials. And one reason why these levels of arsenic and antimony and zinc, they are so high that they exceed the limits of safe use is that the very issue I pointed out in my lecture, that nowadays most smelters in the world, they are recirculating the flue dust back into smelting. So there's no other outlet for arsenic, antimony, zinc than the slag and the anode, and that recirculating back the flue dust is probably doubling or even increasing more the impurity levels of these copper smelting slags, to my mind. And to be how to say responsible company for smelting copper, those flue dust should be treated separately, so that copper is separated from all the other stuff, which is then stored in a safe place, like down in the mine or something. So then our slags would be containing much less arsenic, much less zinc, much less tin, much less antimony, and probably they could then pass these leaching tests for secondary materials, and they could be allowed as the raw materials for cement making or making artificial gravel or aggregates for construction industry. So that is in a way that is that is question of resource efficiency. So if we waste this kind of large volume slag, which could be used for construction purposes, so we are using virgin sand and gravel and aggregates instead of these man-made synthetic ones, which could be equally good in terms of strength and other properties, but now they are not clean enough.
Okay, thank you. So I can conclude that the quality from the electric furnaces slag is not good enough, but the flash converting slag is good enough to recirculate, right?
Sorry, could you repeat that?
Oh, okay. So maybe I can conclude that.
Yes, you can repeat, Nabil.
Okay. So the slag from electric furnace is not good enough to recirculate, but the flash converting slag is maybe the quality is good enough to recirculate to the system. Is that right?
Yeah.
Yes. It
That
contains
is
higher
correct.
copper, right, Pekka? Yes.
Yeah, that is correct. Yes.
Yeah. Because in converting, the oxidation is stronger, Nabil. It's very strong in order to extract the copper from CO2S. Any more questions? We still have 10 minutes. Okay, we have already nice 2 questions. I hope other student will ask. It seems that the active student is like remain the same. I don't know. They are shy or from other university also welcome from Indonesia, from UI, University of Indonesia, or from Yogyakarta, because we have many university here, Pekka. So I expect. Okay, in the chat. Oh, it's just okay.
All right.
Okay. Okay, guys, I wait for until 1 minute or 2 minutes. Okay, there's another question, Pekka, from Daniel. I see there is Chinese technology as one of the method in pie chart for smelting copper. In the last lecture from Professor Longgong, wow, you even know the note from Longgong. Even we still don't send yet the material anyway. The cut off grade for copper in China is as low as 0.2%. How different is this technology from flash smelting? Is it the reason why China can process ore with 0.2% concentration? I mean, the ore not concentrate, I guess.
Yeah, that it's a different thing. The smelting technology and cut-off grade. This 0.2% is also in Europe, in some big open pit mines, the cut-off grade. The important issue here is the grade of the concentrate, as Imam said. So I assume they produce in this, like in Europe, in these big mines having low grade ores, they still produce concentrates which are having more than 20% copper. So it is not very sensitive to the technology used in copper smelting, but this Chinese technology mentioned there are actually actually two technologies which are used in here, and they are bath smelting technologies, which typically are used in rather small smelters, less than 200,000 tons of copper per year, and they obey the same rules as these flash melting and the other bath smelting processes. So nothing very spectacular in there. So it's they are these Chinese technologies, at least the bottom blowing technology, has been well presented in the conferences and journal publications over the last 10 years time, and there is more than 10, probably 15 smelters in China using this for copper. But as I said, they are typically small ones, and the special feature in those that technology, which is called SKS technology, is that they are using special 2 years for introducing the gas below the matte phase, and that gas is rather rich in oxygen. So normal Pierre Smith type of tubes, they are not capable of introducing high oxygen enrichment gases into the vessel. But I think this SKS can use more than 50% O2 containing gases in the system. So they are, by that way, they are generating rather small gas volume, but their feed is wet. So it is typically, I think, filter dry, so containing between 8 and 10% water, which is increasing the off gas volumes very, very much. So yeah, so as I said, there's no linkage between the ore grade and smelting technology. So all smelting technologies can be used for copper making of low grade ores. Only the generated slag amount is larger in cases when the ore grade or concentrate grade is very, very low.
Yes. So yes, as long as it is sulfide, flash smelting can be used, right, Pekka? If the copper content in the ore or in concentrate is low, meaning that you have more slag.
Yeah.
Yes.
Yes.
Yeah.
Some 25 years ago, we did in Outotec's pilot plant, we did flash melting tests for Brazilian company for a concentrate which was containing less than 10% nickel.
Very low. Yes.
So it contains some 3 to 5% copper, but it was the lowest I know.
Okay, guys. Time is perfectly 3 minutes to 12. So thank you, Pekka. Can you select the best questions?
Yeah, best question.
Yes. Difficult?
It is difficult, yes, yes. I think this last one by Daniel was pretty good. Not
Okay.
probably because of what he meant, but it is rather important issue
Okay.
in copper making and in the future copper metallurgy. So low grade and more impure materials are our future.
Okay. Okay, guys. Thank you very much. There, I will give a news. We will email you about the materials and also the link of the recorded video to you. And also for the lecture the day after tomorrow only, which is on 3rd August, we will use Zoom. And after that, we will back to VO meeting again. Because, you know, some area internet is not so good, Pekka, and also some computer maybe is difficult to use for meeting. So we will use Zoom for lecture on 3 August, and we will send you the link. So for
Okay,
the
good.
participant from China, there is no issue because by July this month, Zoom is not blocked. So some of my friends and my colleagues already meet with China's friend with Zoom.
Okay,
Okay.
that's on Wednesday then.
Yes, on Wednesday only. Yes.
Yeah. Okay.
On Wednesday,
Good.
we will use Zoom. Yeah. Okay, guys. Thank you very much. And thank you again for Pekka. Bye-bye. See you soon.
Thank you.
Again
Bye.
tomorrow.
Bye.
Bye. For Danes and Hausan, we test the Zoom, okay? Now I'm waiting for you in the Zoom.